Hello， 大家好，今天来讲一下我是电教的这一个问题，大家可以看一下，也就是说，为什么 r squared 在某些情况下会是 negative 的，就是小于零的。Sometimes r squared could be greater than 1。尤其是当你这个 regression 没有 intercept， 就是 y-intercept 的时候，就是 y equals b0 没有 b0， 直接是 b1 x plus error。为什么在这种情况下更容易出现negative r squared 的情况？这是个非常好的问题。Believe it or not， 我录了2次视频，第一次45分钟，第二次50分钟，所以我想把它截成3段来发，就是3部曲吧。首先，今天的这个视频大概不到10分钟，一个前序吧。你能怎么样去理解 r squared？ 其实 r squared 有各种各样不同的理解。我之前在讲 ANOVA 的时候讲过一个其中的理解，但今天是换了另外一种思路来讲 r squared。为接下来要讲那种 negative r squared 或者是没有 y-intercept regression， 怎么样去看这个 model fit 的 data， 做一个很好的铺垫。所以okay, without further ado, let's get started.
Okay, so if you want to estimate the value of y, suppose you randomly select this many students. You observe the value of y, which is test score. So maybe this is a 90, this is 100, 80, 85, 95, like this. And based on this y, right, this values of y, I can calculate y bar. Suppose y bar is 85. So this y bar 85 is actually the point estimate of population mean, right? Or if y bar is representative, we can call this y bar typical value, right? Or in other words, if I randomly select a student, my best estimate of the student test score can be 85. If I randomly select a student, if you ask me what is the estimate, what the score the student could have, or can you give me expected test score for this student, I can give you 85. 85 could be an estimate. If I use 85 to estimate y, so the estimation error would be, I can draw this kind of graph. So this is y, no x, in this case no x, but I just put y on y-axis, but there's no x. There's no explanatory variable, right? No x, but I just want to make it comparable to the later case. So y, let's suppose y bar 85 is here. So I have this y, the value of y, maybe somewhere here. And y bar is here. So if I use y bar to estimate, to be the estimate for each value of y, we call this observed value. And estimated value, I can just use my y bar. I can write this estimated value, just use y bar. So that's y bar could be 85, 85, 85. So this could be my predicted value of y. This is actual observed value, this is predicted value. This actual observed value, this is predicted value. If you randomly select student, you know the student test score observed value, true value is 80, but I give you the estimate 85, right? The difference is estimation error. So if I use y bar to be my estimate of each value of test score, and the estimation error should be each value minus y bar. Or if I use y bar to estimate that, the difference is this. Y bar minus y1 squared. Y bar minus y2 squared plus y bar minus y sub n squared. So this actually is the sum squared deviation from the average, right? Y bar minus y sub I. Or squared each value deviate from its mean. Graphically, that's, if I draw this is average, and the deviation will be this much squared, plot this line squared, plot this line squared, plot this line squared, right? That's the deviation, that's the estimation error, squared, this is the estimation error. If you're using y bar to be the point estimate for each observation, each value of y. Let me just use this circle. Right? So this is observed value, this white little circle, and this blue line represents the estimation error if you're using y bar to be the predicted value of y for each observation. This is actually total variation, sum of squares total variation in y. In other words, you just use y bar to estimate the value of y, right, for each observation. But instead of doing this, I can be more precise. I can provide a more precise, more accurate estimate for each observation, for each value of y. I might have an explanatory variable. I could call it x sub I, maybe study hours. So study hours, maybe this person 30 hours per week, and this is a 25 hours per week, and 28 hours per week, and this is a 20 hours per week, 15 hours per week. So if you ask me for the first person, you know this is observed test score. This is what actually happened. So the first person test score is 90. But if you don't know the value is 90, you want to estimate this value. One solution is use the sample mean as an estimate of 90, right? The estimation error is 5. Or you can be more precise. You can use study hours to provide an estimate for the value y for the first observation. So, and now you need to find the relationship between study hours and test score. So let's assume that is our only assumption is we assume there's a linear relationship. Linear relationship run OLS, maybe it's here. Linear relationship OLS. So now this is any point along this line is a predicted value of y, right, y hat for a given value of x. Like this. So now I have this y hat equals b0 plus b1 x sub I. And now we can get a predicted value of y, right? Only the predicted value of y only depends on x. We plug 25 into this equation and I get a predicted value of y. Maybe this is 89. Just for example. This plug 30 into this equation, we get a predicted value of y. Maybe it's 98. 15, 79, 20, 86, 28, 93. So now if you ask me, what are the predicted value of y for the first observation? I can give you this value, 89, right? It's better than 85 because the estimation error is a lot smaller. The estimation error between the true observed value and the predicted value is only 1. But if you're using y bar as estimate for this value, you see estimation error is 5. So this provides a better estimation, right? If I use y bar to estimate the value of y, I can get the estimation error. So now let me write it here using this pink color. So using y bar to estimate y, error will be predicted value minus observed value, right? Predicted value minus observed value, all the way to predicted value minus observed value squared. You see, what is this? We said that this equals sum of squares error. So that's a variation in y explained by the error, right? That's sum squared predicted value y minus observed value y, which is sum error squared. So you just focus on this expression. That's actually give us the estimation error if you're using this x as a predictor, right? So if you use x as explanatory variable, this will be the estimation error, right? This is a total variation estimation error. You plug error squared, right? I'll add this up. So now you should just compare this with this, right? You compare this with this. This is definitely smaller. This is larger. So sum squared total, sum squared error. So R squared is defined as 1 minus sum squared error over sum squared total. Or the difference sum squared total minus sum of squares error equals sum of squared model, that is variation in y explained by the model. Or in other words, you can write R squared as sum of squared explained by the model divided by SS total. So sum square model is y hat minus y bar squared. We talked about that before. So that will be the deviation from the estimated value, which is on the line, and y bar. That's, you see, so this is less dispersed, right? This is sum square model, which is definitely less than sum square total. So you have this is a fraction which is less than 1. If all the points line up on the same line, that's less than equal to 1. So sum square error we just said is definitely less than sum square total, so there'll be less than 1, and the whole thing is less than 1 or equal to 1, right? R squared, like this, right? So in this case, we know that R squared gives us the fractional variation of y explained by x, right? Fractional variation of y explained by the model, which is between 0 and 1 inclusive. Right? But now to understand in what situation you have a negative R squared, just use this logic, a negative R squared. So I'm giving you this, a negative R squared.
I hope you find this helpful. And 接下来我们就要下一个视频就是要讲一下，就如果没有 y-intercept 的时候，可以说是一个核心内容。为什么没有 y-intercept， 你可能会得到一个 negative R squared。然后我们会把它解释成这个 model。它的 predictive power 会 even worse than a horizontal line， 就为什么这个 model 它没有一个均值来解释这个 y 解释的好。OK，stay tuned。So 我们下一期视频就讲一下为什么就是怎么样去理解 R squared，当你没有 y intercept 的时候。OK，so thanks so much for watching. I'll see you next time. Bye.